Okay, so hi everyone. My name is Raul Gracia. I'm principal engineer at Dell EMC, working on the Pravega project, which is an open source storage system for data stream. And I'm going to, give this talk about data streams, auto scaling of streams, and its connection with serverless computing. So, not much to perhaps nothing new for you probably, but serverless computing and data streams are a great match. Serverless frameworks provide us like the ability to trigger functions in response to events, and they provide a great deal of abstraction of the underlying infrastructure and a simplified programming model for users. And at the same time, we have data streams that are conceptually a continuous source of events, which looks like an ideal input for serverless computing frameworks. And we have to take into account that data streams are becoming a first-class citizens abstraction for many use cases in the real world, in customers, such like objects or files. And one example of this synergy between serverless and streams is that we can see out there. It's frequent to see serverless frameworks like OpenWhisk or Lambda having connectors or allowing you to consume messages from Kafka, for example, right? And the popularity of data streams and serverless, right? So, for example, at Dell EMC recently in the Apex Private Cloud, which is a new offering from Dell, we are now able to deploy Knative as a service, right? So it's just like another data point of the popularity of this kind of computing model and how it can actually solve problems in real customers. We have many of them that are use cases that are working with the streaming data platform, which is a product from Dell EMC, which is providing streaming storage with Pravega that I'm going to introduce next, plus analytics, right? And we can have we have multiple cases that data streams made of drone images, video analytics, and sensors, IoTs in factories, and perhaps not all the use cases, but many of them perhaps could be solved or addressed easily with serverless computing. Of course, here I'm going to focus more on the source of data for serverless framework, which is Pravega. Pravega is a storage system for data streams that is an alternative to Apache Kafka or Pulsar that perhaps you are more familiar with, and it has like several distinguishing design decisions that makes it like a brand new system that offers like different capabilities to existing counterparts. So let me introduce Pravega. We'll start with some concepts. So again, Pravega is an open source storage system to serve and store unbounded data streams, and which is basically an abstraction that is an append-only sequence of bytes. So data in a stream cannot be modified, but it can be truncated. And then we have writers, which allow us to, and readers that allow us to write and read data from Pravega streams. Of course, we cannot have an infinite piece of data, right, for a stream. So basically, in behind the scenes, internally, Pravega splits a stream. The abstraction of a stream is built into segments, which is the basic unit of storage in Pravega. So basically, a stream can be understood as a sequence of segments. Segments can be in two states. They can be open, or which means that we can write data that can be consumed by readers, or segments can be sealed, which means that they are read-only. One of the distinguishing features of Pravega is that it is a tiered storage system, meaning that Pravega is designed based on the assumption that you want to keep your data forever, right? So in a cost-effective way. To do that, Pravega has a tiered design. So we have two storage tiers. When a writer writes data to Pravega, we first write it to tier 1, which is a distributed write-ahead lock, which provides low latency and durability of messages. And asynchronously, Pravega is grouping those events into larger chunks and moving them into what we call tier 2 or long-term storage. And so basically, we have low latency tail reads for applications like serverless frameworks consuming those events. And if we want to do a batch job on that data, we also achieve high throughput. One more important characteristic of Pravega is the write-read parallelism. So basically, in Pravega, we can have multiple parallel segments to write data to and to read data from. And apart from that, another challenge that Pravega solves is to provide write and read guarantees. Those are extremely important for making sure that we are not missing data or we are not losing events, and at the same time that what we read at the other end is consistent. So Pravega provides exactly one semantics. There are no duplicate events or missing events, even though there are reconnections, and total ordering of events per routing key and per writer. And at the reader side, we also guarantee that there are no duplicates, no missing events, and so on. So this has been like a super quick overview of Pravega. And just to wrap up, so why Pravega compared to other streaming system or storage system for streams to consume data from is that it provides unlimited retention from its design. It allows, with the same system, it handles real-time analytics and batch analytics. It provides data durability, parallelism, and guarantees for reading and writing data, right? But in particular, because in the previous talk we heard about scaling and so on. One distinguishing characteristic or feature of Pravega is stream auto-scaling, right? Of course, I mean, in a data stream, we cannot assume that the load is going to be constant. There would be load variations on a stream, daily patterns, and so on. So ideally, a data stream should basically vary the parallelism of the stream, the number of parallel segments, accordingly to the load, right? So this is a feature that I am not aware that any other system has, which is auto-scaling. In Pravega, we can define stream policies, scaling policies on a data stream, such as if a segment gets more than X number of events per second, then we split it. And basically, Pravega tracks this with a feedback loop and automatically triggers scaling up and down segments. So this is a kind of conceptual representation of that. You can see in the image the key space of routing keys, which goes from 0 to 1. Initially, this stream has a segment 0, which is a single segment that is handling all the load. And after some time, the system detects that this segment is becoming hot, so it decides to split that into segment 1 and segment 2, which are basically getting half of the key space each. And as you can see, the process continues until it stabilizes, right? This is a real view of what it is stream auto-scaling in Pravega. We induced an experiment with a variation in the number of events per second we were writing to a stream, and this is the lower graph that you see representing the load. The upper one is a heap map representing the parallel segments at each point in time of that stream, and the color is the load, right? So you can see that when the load goes from higher to lower in the middle region of the plot, the number of parallel segments is reduced, and when it goes up again, we can see again splits of segments into multiple ones, and then we have more parallelism of this stream. This is done completely automatically. Neither the application or the client it realizes about that. So then I wanted just to try to connect the dots just to complete the presentation, right? So on the one hand, we have serverless frameworks, which are easy to use, very popular, and they take care for us to scaling up and down computing instances. Some of them, perhaps, for example, would be based on resource metrics like CPU. But at the same time, we have now data sources like Pravega streams, which can vary the parallelism of a stream a long time, which is a new software-based metric that can be used to scale upon, right? So the idea that I wanted to share with you here is that perhaps we could explore, if that would be interesting to use the parallelism of a Pravega stream as a hint or as an additional metric to inform the serverless computing framework in order to be able to scale up and down, in this case, based on this new software-based metric. This idea is not new because we already have a success story for Pravega and Apache Flink. Today, we can basically automatically scale the parallelism of an Apache Flink job based on the number of parallel segments of a Pravega stream. And I thought that could be interesting to start an exploration whether that would make sense in the context of serverless. So yeah, that's it.